fellow Stephen, physics and math teacher, taking you through the tutorial of new lower secondary physics, competency-based physics, paper 535/1, a paper that is compulsory to all students offering physics in O level. So it is a must for whoever is doing secondary, lower secondary. It's a must for him or her to do and actually to offer this, to register seat for this paper. So I welcome you all to my channel, and I believe by the end of today's discussion you must majestically march away with something. So without wasting any microsecond, let's get into the gist of discussion. Now the issue is we are discussing a sample item coming from the first theme. Think about it. Which theme is that? Who can predict the first theme? And if you missed the first presentation about the introduction of this paper, kindly check the videos there. It will give you the introduction, it will give you the description of the paper, how it's marked, it will give you the element of contrast, the so-called themes, the topics that we need to cover, in which term, in which class, and how many items, everything is there in the first video. Kindly check for that video, and every time you watch these videos, please don't forget to like, subscribe, comment and share. By so doing, one, you will be securing yourself from receiving daily updates. Two, we shall be promoting our channel to another level. So it is just a service either way. Today's discussion, the theme is 1, 2, 3. The theme is light and waves. So the sample scenario is coming from this theme, and let's have a look at the sample scenario. This is a sample scenario. Now I always advise my students to do this. This is my opinion. Every time you meet a scenario, first check on the tasks. First check on the tasks. What is there? What is there on the tasks? I can see they are talking about rainbow. Difficult to see the colors in the rainbow. I can see they are talking about telecommunication. They are also talking about production of sound. Meaning, as I get into the scenario, remember, not every word in the scenario, every letter in the scenario is counting an addition to the responses you need. They are relevant words or statements, and others are just backup statements to make the scenario look realistic, look vivid and valid. So that's why I advise you to sieve or check. Look at this scenario. Two holiday makers secured permission to go and check on their grandmother who stays 2 villages away from their homes. You see, the whole of this is a backup statement or backup sentence. We continue. After a while, it started drizzling. I'm starting to believe something, because every time it drizzles, we see a rainbow. Is it every time? Now that's a topic of discussion next time. But in most cases, it starts to drizzle, we expect a rainbow. Okay, immediately after a while it started drizzling, and their mother called the grandmother to find out if the visitors had reached safely. Guess what? The holiday makers. The holiday makers were surprised to see a rainbow. I told you part A is already covered. A rainbow. But the grandmother could not explain the origin or cause of the rainbow. Meaning at some point you will be required to explain how a rainbow is formed. What causes a rainbow? And that's part A. They also remembered that their P7 teachers had told them that it has 7 colors. Oh, at some point we'll explain how the seven colors come, which they failed to prove by counting physically. At some point we'll explain why it is difficult to receive the clear view of this, and one gets into position to count them. We continue. In the evening, an old man in the village entertained them with music produced by a one-stringed instrument. How music or how sound is produced. When you pluck a guitar string, how do you receive sound? Can we explain this? And this instrument was called a tube fiddle. They wondered how one string can produce different notes by pressing his fingers at different points on the vibrating string. Don't you think my scenario is done? All the tasks, formation of the rainbow, difficulties in differentiating the colors of the rainbow, telecommunication, how communication is possible. Remember, the mother called the grandmother to confirm whether the Jadens had already reached safely. And also, when the Jadens reached home, at the grandmother's place, there came an old man with a tube fiddle. And to their surprise, they were wondering how this guy was producing sound. Every time he plucks at the same string at different points. So by the end of the day, you get to realize that the scenario is already at home, and we are also at home with the scenario. Now we have to just move to the solutions. In other words, the responses as per the new curriculum. Let's meet there on the responses and we see how to discuss that. Thank you. Thank you so much. The task requires us to explain how a rainbow is formed. Now, a rainbow is formed by four processes, and the processes are refraction, bending of light ray as they pass through a pair of substances or medium of different optical densities. For example, air to glass, glass to air, water to glass, water to air, etc. Now this can also be defined in terms of speed or velocity, is the ratio, in terms of change in speed of sound or of light. So refraction refers to the change in speed of light as it penetrates or it passes through a pair of medium of different optical densities. Then if we are to use this example 1 and 2, we can see that here a ray is coming from air and it is entering a glass block. Then here it is from water and it is entering an air interface. So as a ray is moving through air entering a glass block, it bends towards the normal. You can ideally see that this angle of refraction, which is the angle between the normal and the incident ray, is actually smaller than the angle of incidence, actually, which is the angle between the normal and the incident ray. This is the refracted ray, sorry. Angle of refraction is the angle between the normal and the refracted ray. Then angle of incidence is the angle between the normal and the incident ray. So since air has less refractive index compared to glass, because air has 1.0 approximately, then glass 1.5, depending on the glass block, dimensions of the glass block 1.5055. So get to realize that air has less particles that are far apart, and for that reason a ray does not lose much of its energy while penetrating through it. And on trying to navigate the glass block, it passes with sufficient energy, and therefore its speed is not affected as much, because if it had already 100%, it might flock through the glass block with a velocity whose energy is about 90%. So that's why it does not bend away from the normal. Then for this second case, you can see that a ray is majestically propagating through a block, and after a while it is refracted away from the normal in the air interface. Now we agreed that water has a refractive index of approximately 1.33, and then air has still 1.0. Remember, refractive indices or index do not have units. Now the angle of incidence in the water is smaller than the angle of refraction in the air. This is because water has molecules that are moderately packed compared to the molecules of air. So for any propagating ray experiences a reduction in its energy of motion vis-a-vis the speed of, or this velocity of motion. And on trying to penetrate the second medium, it does this with less energy, and this manifests in form of failing to maintain the same strength path as the 90% of the energy. If it had 100%, as let's say 60% of the energy is lost, and the 20 or 7 60, then 40% or 30% is refracted, so it bends away from the normal. So this process of bending, whether towards or away from the normal, is what we call refraction. So for a raindrop, a ray is coming from air and it's penetrating, or it's trying to navigate the water drop. So we get to realize that bending of a ray will take place inside and outside that raindrop or the raindrops. Next thing is dispersion. Dispersion simply means splitting of the white light. When this white light meets a glass block, it splits into its components, and the component colors of white light are red, orange, yellow, green, blue, indigo, and finally violet. You can call this you can give acronym of Richard of York gave birth in vain. Gave birth in vain. Just memorize the 7 colors. Now, to give you a smaller description of how the 7 colors are formed by the process called dispersion, you can see here white light incident on one interface of the glass prism, and it is refracted with different rays meaning of different wavelength, and on the final interface you get to see that the splitting or the dispersion of white light vividly manifests on this side, and we get the red color of light ray with approximate wavelength of 760 nanometers, and then the last one violet of approximately 380 nanometers. So as you move from red to violet, the wavelength keeps on reducing vis-a-vis an increase in the frequency. Now, because we agreed that frequency, we agreed F, come here, F is equal to V over lambda. Now, where V is velocity of light, and then lambda is wavelength, and then F is the frequency. Now, if you check on the relationship between frequency and wavelength, actually frequency is inversely proportional to wavelength, meaning every time wavelength reduces, frequency increases. So when wavelength reduces, frequency increases. So that's the relationship, and it happens in such a way that red has the highest wavelength with the smallest frequency, and violet has the smallest wavelength with the highest frequency. So that will help us understand dispersion. The next thing is total internal reflection. Total internal reflection simply means a phenomenon where all, if I can describe it from here, a phenomenon where all the energy incident on an interface, for example between air and glass, where all this incident ray is refracted. And the question is, what brings about this phenomenon? This is angle of incidence, and then this is angle of reflection, not refraction. So what happens is that as a ray is moving or propagating a more dense, optically dense medium, some part of a percentage of its energy is refracted, some percentage is refracted and some is reflected. But now as we increase this angle of incidence, as we increase this angle of incidence to a point when it is now the critical angle, the ray all of it merge and propagate or move along the boundary. So for that case, all the refracted ray is taken to be a grazing ray, meaning the angle of incidence instead becomes 90 degrees. Okay, as we continue to increase this ray, increase the angle of incidence to a certain angle I, of which this angle I is still greater than the critical angle, then all the ray that has been grazing, all of it start to do what? To bounce back within the same optically dense medium. So this phenomenon gives a manifestation of the ray being totally and internally reflected. So you can see the bouncing back of the ray. The ray is bounced back within the same medium. So that is how total internal reflection occurs. That's how it occurs. Okay, that's how it takes place. Next, scattering. Now scattering, we can use this very what? We can use this very prism to show the scattering. Now the scattering is just spreading distribution of these 7 colors, that is from red to indigo. That's the scattering. And once you see this in the sky, the scattered 7 colors that are in an arc, circular shape arc, or in a disc shape, then that is a rainbow. And what brings about that disc shape is the shape of the atmosphere or the shape of the sky. The sky is spherical in nature, so the formation of the rainbow or the shape of the rainbow is given by that sky. Alright, now it is also possible to have, just like you can see our rainbow here, it is also possible to have these 2 rainbows. One is quite clear, this is number 1, and there is this one, number 2, kind of faint. So you're going to research, and I want to get your answers on the comment section. Kindly explain, why do you think we have 2 rainbows? One is clear and the other one is faint. Otherwise, let's move to the next slide. Thank you so much. Part B requires us to explain why it is difficult to distinguish the colors or differentiate the colors of the rainbow. Then part C wants us to explain how satellites help in the communication process. Now part B, there are only 2 issues that bring hardship in distinguishing these colors of the rainbow. One is the impurities in the sky or in the atmosphere. These impurities are as a result of a concentration and accumulation of smoke, dust, and so on in the atmosphere, making the spectrum impure. And anything that is impure means the observer find that thing hard to observe or to read. Then the overlap of the colors bring also that hardship of distinguishing. The overlap here means these colors tend to mix up, and for the observer receiving this color, find it hard for him or her to distinguish them. So there are majorly two issues here: imputing the spectrum formed, that visible spectrum formed, and also the overlap, color overlap. Then part B needs us to explain how satellites help in telecommunication. Now the satellite you are seeing here is just an example of it that I've given you. So this satellite here is launched in the space or in the atmosphere, depending on its purpose. Now we have majorly two types. We have the man-made satellites and the God-made satellites. Satellites are just objects that revolve in the orbits of the atmosphere. So these objects can be man-made, of course depending on the purpose. If it's made for communication, then that is a communication satellite. If it is made for detecting weather satellite. If it is made launched for security purposes, that can be military satellite. If it's launched for navigation, that is navigation satellite, of course, the one that we use for telling the GPS the location of different places in the continent of a given, in the world. So now for the case of this scenario, they want us to talk about the communication satellite in particular, and to check on it clearly how signals or how the information is picked from the phone of the sender, transferred to the satellite, how it is got from, if for example here is the sender, this is the satellite, and this side is the receiver. How this information flows from the sender to satellite, then back to, from the satellite to the sender. So what happens here is that the sender produces sound for the case of a phone call. So that is the mother who is acting as the center at this point. Speaks, makes a sound, and this sound is in a form of energy. Now this sound energy is converted into electrical signals that are suitable for signal transmission, that are suitable for transmission to the satellite. Now these signals reach the satellite by the help of the uplink dishes, or the uplink dish. Now the uplink dish is a telecommunication component that helps to transfer the electrical signals to the satellite in the sky or in the space. Now at the geostationary satellite, or at the satellite in the sky, these signals are now converted into waves or radio waves. And now, just like you're seeing these waves, Mayengo in Luganda, these ones here, they are waves. These ones here are waves. Now they are converted into radio waves. But now to reach the dish, or to reach the phone of the receiver, these radio waves are still converted into electrical signals. But before that, they are first received by the downward links or dishes. They are the ones that convert now the radio waves into signals that are received by the phone of the receiver. So for this case, we can say that the grandmother is the receiver, who is having the phone that receives the radio waves, and these radio waves convert these radio waves to signals that are received by the grandmother. So the process is complete by the help of one, the phone the receiver has, that converts sound energy into electrical energy, and this electrical energy accelerated to the geostationary satellite or the satellite in the space by the help of the uplink dishes or dish. Now at the geostationary satellite, the radio waves are converted into electrical signals that are transferred or transmitted to the ground by the help of a downward link dishes, which convert this into sound waves again. So the observer or the receiver at the ground, on the ground, perceives the sound by this help. Now for the case of a broadcast, maybe a TV, it is the same story. Taking this point A as the point of broadcast or broadcast center, this is point B, the point where people are receiving the broadcast. So what happens is very simple. At the broadcast center, whatever they are doing, let's say there's a match here, match taking place, Man City or Arsenal versus Man U. What happens on the ground or at the station or at the stadium is that there are cameras, there are gadgets that they use to capture at this occasion. Now these cameras convert those pictures, those audios, those videos, and all the images captured at the center. They are converted into electrical signals for easy transmission to the satellite. So these electrical signals are accelerated to the satellite by the help of the upward link dishes that accelerate the signals to the geostationary satellite. Now at the geostationary satellite, the received radio waves are now converted into electrical signals, and they are transferred to the satellite dishes, also called the downward link dishes. And at the downward link dishes, they transmit these electrical signals to the TV or to the DSTV dish, and the DSTV dish converts these electrical signals into videos, audios, photos, and images. So in this process, the observer, the receiver at point B, is in position to receive the live broadcast right from point A by the help of this communication satellite. Well, thank you so much. Allow us move to the next. But before that, let's first erase this literature. Let's first remove this information. We need to leave our work clean for further explanations, for further So let's first make our look clean. So sit down, memorize about this process, write something. For any question, please, I repeat, post that question on the comment section. Don't forget to like, share, and subscribe to this channel. Thank you so much. Let's move to the next slide. I need just to explain how sound is produced by vibrating string. Now, sound note produced depends on very many factors. Taking a case of a string, a factor number one is the length of the string. The length of the string affects the sound produced by a string. The applied tension, that plucking force applied on the string, also affects the sound. Now what happens here is that when a string is plucked, or when the force is applied on the string to make it vibrate, it produces sound. Well, but now every time you change the position of application of the force, the vibration keeps on changing, or the sound note is produced with different pitches. And we agree that a pitch is just a perceived highness or lowness of sound energy. Now, there are very many factors that affect this component called pitch of sound. And among the factors we have frequency. And we agreed here that the higher the frequency, the higher the pitch. In other words, in 1 second, if a string can produce as many as possible complete cycles, then it means that that machine can give a higher pitch. So the higher the frequency, the higher the pitch. On the other hand, the lower the frequency, the lower the pitch. So if a string makes very few oscillations in 1 second, then that string gives a lower pitch. Okay, another factor is the length of the string. The longer the string, the lower the pitch. Think about it, having two strings, one is long and the other one is short. We use the same force to pluck both of them. You're most likely to perceive a very sharp and clear sound from the shorter string. That's why the shorter the string, the higher the pitch, and the longer the string, the lower the pitch. So you can see a shorter vibrating length produces higher pitch, while a longer produces lower pitch. So through all these processes, we get to realize that a string can give a note, a sound note that can be perceived by the observer or the receiver. Otherwise, thank you so much for
in the dark of night, the stars light up the sky. We see them flying free. That's just like you and now